failing me.
Okay,
Good morning,
stop.
everybody, and welcome back to Abstract Algebra.
Stay
The mouse
safe
is
from the
fine.
campus.
Technical
Hi,
difficulty.
Yeah, of course,
This is
big
Abstract
excuses.
That's it.
So, plan for today, we're going to talk about UFOs. Oh wait, that's a D, just poorly written. We're going to talk about unique factorization domains and irreducibles and all that jazz. And in essence, kind of fill in the last major type of intermediate type of ring between integral domains and fields today. I've got my usual office hours this afternoon, 1 to 2, tomorrow at 11, and tomorrow at 1. Homework 2, don't forget, is due this Thursday. And there's a homework 3 now posted as of yesterday afternoon that will be due Thursday a week. Yes, Eleanor?
Will you be here after 2 today?
A little bit after 2, yeah. Not super long after 2.
Got one here?
Looking at Peter Jennings, he was supposed to be in 112, and that's not him.
Oh, are you sure you're in the right building?
Is this Dow?
Dow Science.
Okay. Is there a Dow?
There's a Dow Center that's like if you go
Right.
up the hill there.
This would be a classroom.
Which room did you say?
112? So 112 is down the hall. There's math lesson there.
There is a, I mean, Stroh's like 112's room, but he's talking about that. So.
Wait, isn't 112
112's a room. Yeah, it's one of the computer rooms in Stroh's Hacker.
Well, yeah, what's it here?
What is it here? I have no idea.
The classroom.
This is what your room
Dow 112. For meeting for CCA. That's likely. I'm guessing that might be the Dow Center, but I'm not 100% sure. You know, I'm going to contact him just to check. Thank you. Where was I? Anyways, homework 2, due this Thursday. Homework 3, due next Thursday. Homework 1 has been passed back. If you go look on Canvas, I actually have my own personal solutions posted for homework 1. So if you're not sure why I dislike something that you said, or want to see how I approached a particular problem, because there's a few ways you can approach them. Number 2 in particular on this one could be approached several different ways. I encourage you to check that out. Yeah, any questions, comments, or concerns before we get going? How does a mathematician, double timing as a witch doctor, remove curses? A mathematician witch doctor can remove curses by spinning around in a circle, clapping 3 times, and shouting, "Hexagon."
I figured it would be a hex joke somewhere.
Oh, of course. Hexadecimal, I don't know. Alrighty, so, if you're a computer scientist. So last time, at the end of class, we had finished kind of our general discussion of Euclidean domains. And we had seen that we sort of have this hierarchy of field implies Euclidean domain, implies PID, implies that you're working over an integral domain. And what I want to do today, I want to find something that goes here. And this is going to get into some other property of the integers, not directly related to using the Euclidean algorithm or that any ideal can be generated by a single element. But today, we're going to be talking about how in the integers, any positive integer, well, any integer other than 0, 1, or -1 can be factored into primes in a unique way. And we're going to be talking today about what are rings like, what are some other rings in which that happens, how does that actually give us something that goes nicely in our diagram here, and we'll also talk about the most important woman in mathematics. That's the plan. Alright, so last time, at the end of the last class, we started talking about UFDs. Does anybody need a packet? Okay. And which we defined irreducible elements, where we said that an element, a non-zero element in an integral domain is called irreducible if it's not a unit, meaning it doesn't have a multiplicative inverse, and whenever you can write A as the product of two elements in your integral domain, one of those elements has to be a unit. So there's no way of breaking down A into two factors where neither one is a unit, or the simplest type of element in the integral domain, so to speak. So last time, we looked at a few examples of these. So like in the integers, for instance, we said that our units were just plus or minus 1. And so what did we say? That n is going to be irreducible if and only if what happened?
If n is prime.
Yeah, if n is prime. Yeah, prime numbers. So like 2, 3, 5, 7, 11, 13, negative 2, negative 3, negative 5, negative 7, negative 11, negative 13, etc., were all numbers that have these properties. The only way to write it as a product of two other things is if one of those things is either 1, you can either write p as 1 times p or negative 1 times negative p. And that's the only way to write p as the product of two integers, assuming p is prime. Whereas if p is not prime, like 4, there's other ways to do it, like 4 equals 2 times 2, for instance.
Are there rings made up of entirely of primes and irreducibles?
Made entirely of primes and
Sorry, irreducibles and units.
irreducibles and units, sure. Would you like an example? And well, you also need 0, yes.
That's pretty close.
There you go. It has 0 and a single unit, that would be a ring. Are there any interesting rings where that happens? I don't want to spoil that one. That's an interesting question. Most rings, though, are going to have irreducibles and non-irreducibles, at least out of the ones that we're going to be studying. Z mod PC, if you want to generalize, by the way.
Yeah, that's what it was.
So, how about the other kind of major example we looked at is the real polynomials, where last time we said units are going to consist of any constant term other than 0. Why? Because anything that has an x in it is automatic. Any polynomial that's non-constant over the reals is not going to have a multiplicative inverse, because you need rational functions for that. But any non-zero c, you can just multiply by 1 over c to get to 1. And as our example, we said, for instance, something like 2x. Is that irreducible? I would say so. There's a lot of ways you could write 2x as the product of two things. You could write it as 2 times x, or 8 times x over 4, or however, a lot of ways to write this, but there's no way to write this where both terms are non-units. In this case, this would be a unit, that would be a unit. 2x, it turns out. If you want to write it as a product of two things, it's always going to be some non-zero constant times some non-zero constant times x. And the non-zero constant by itself is always going to be a unit. So what's something that would not be irreducible? Real polynomial land. Parker.
X squared.
X squared. What's a way to factor x squared in a way that doesn't use that uses two non-units?
X and X.
X and x. X squared is a big old x, for it is not irreducible. Now, you can write x squared in a way that uses a unit. You could write it as, for instance, 2 times 1/2 x squared. But the fact that there exists at least one way to factor x squared into two non-units makes x squared non-irreducible. or dare I say, reducible. Contrast that with integer polynomials. Is 2x irreducible there? Isaac?
Then you just do the same thing, but all the constants aren't. So 2 times x is one way to write it
As a product of
2 non-units.
two non-units. Yeah, so here 2x is not irreducible, mainly because we have much fewer units to work with, so it's a lot easier to write things as a product of non-units. Here our units would only be plus or minus 1. So the moral of the story is, if you're asking whether something is irreducible or reducible, it depends heavily on the ring in which you're working. Because there are things that are irreducible over the reals that are not irreducible over the integers. And vice versa, Dr. Durston? Turns out no, for reasons we will be exploring. So that's what we had covered as of Thursday's class. Gosh, I feel like I need to do a lot of review when the last class was 5 days ago. Any questions or comments about what irreducible means before we move on to some of the juicier stuff? So it turns out there's a nice theorem which I'm not going to prove because I don't really feel like it. That kind of categorizes that gives some equivalent conditions over a PID at least for irreducible elements. It says that if D is a PID, then the following are equivalent. Turns out P being irreducible is the same as saying the ideal that P generates is a maximal ideal. But Dr. Gerstle, in the packet it says a maximum proper ideal. Yeah, that's what a maximal ideal is. That wasn't a typo. That's me being nice to students who don't necessarily know what maximal ideal means. And condition 3, D mod ideal generated by P is a non-trivial. All right, Matthew. If you had to guess, what would you guess a maximum ideal is in a ring?
Probably the largest ideal that there is. So
The largest that there is.
So like, cardinality. Wait. Yeah, that's the proper way of saying that, right? Cardinality being the largest, or would it be the number of elements being the largest?
I don't think that's going to quite work, because if we were to look at the integers, for instance, literally every non-zero ideal has the same cardinality as the integers.
Right.
So it's not necessarily just strictly looking at number of elements, although you're thinking along the right track.
If you have an ideal that contains, any ideal that contains the elements of that you're talking about, if it's maximum, then the only one that makes an ideal that's bigger than the one you're working with is the actual
Is the whole ring.
ring itself. Yeah.
What do you mean bigger than?
Well, bigger than as in does it have more elements in it?
In terms of like set inclusion.
Yeah.
Yeah, so here when we say that the ideal generated by P is a maximum ideal, what we're really saying is if the ideal generated by P is contained in some other ideal, I, then the only ideal that can contain that is either the same ideal that you started with or the entire ring. there's no other ideals for which this ideal is a subset, in other words, other than literally the entire ring.
And we're saying it's proper, so it's not I.
So it's not what?
Or you could just say if P is properly contained in I,
Yeah.
then I equals D.
Yeah, like we're saying it's proper, so it's not
Okay,
a set.
sure, we could say it in like any number of ways, yes. Yeah, that would be another way you could say it. Proper here just means it's not the whole ring itself.
Is that less than or greater, or less
This
than
right here?
equal to, or is that contained?
This is a subset of, so it's contained in. Yeah. If the ideal generated by P is contained in some other ideal I, then I either has to be the exact same ideal or the whole. There's no way to make it bigger to throw in more elements and have it still be an ideal without necessarily getting the entire ring. Does that make sense? So let's look at an E. So I don't want to prove this theorem. Those of you who had an E for 410, I think we proved, forget what exactly we proved. I know we proved at least part of this. I know we proved at least 2 and 3 are equivalent. I forget if we proved 1 as well. I kind of want to say no.
You talked about one.
Okay.
You didn't really say.
I think we just assumed one and
Yeah.
proved that 2 and 3.
I think we just proved 2 implies 3, and then I mentioned this is equivalent to some other condition called being irreducible.
And then you talked about lying to children, and then
Oh,
there was
yeah,
one
that was
second.
right.
Oh, I did that a lot.
Yeah.
So let's look at a example here, and our ring's going to be real polynomials. So
That's not the one.
let's look at x squared plus 1. Emily Rose, is that irreducible in our ring? Yeah. The only way you can factor it over the complex polynomial land is x plus I times x minus I, and that is illegal in this ring. Don't do it, unless you want me reporting you to Dr. Arm.
I feel like in that case, Dr. Gabler would be scarier.
Could report you to Dr. Gabler. Would that be scary? I don't know. He's so mild-mannered. I feel like
Well, yeah.
You don't want to make
that.
that.
it takes a lot to make Dr. Gabler angry. You know where it really takes a lot to make angry? Dr. Hutchins. I've seen it once. It's terrifying. So according to this theorem, what that means is that if we were to take the ideal generated by x squared plus 1, so this being the set of all polynomials from which you can factor out an x squared plus 1, it's maximal. It can't get any bigger without being the whole ring. Not bigger in terms of like cardinality, but in terms of there's no other ideals that properly contain this one other than the entire ring. And that's equivalent to saying that if we took our ring and we modded it out by this ideal, that's a field. Question. What is this isomorphic to? This potion ring? Does anybody from my 410 in particular remember this one? Because we had this one. Or anybody who wasn't in my 410. Anybody else wants to jump in? How disappointing. It's isomorphic to the complex numbers.
I do not remember that.
I don't remember that either.
Oh, maybe we didn't do it.
I was like,
I thought it was
Very
good.
sad.
I didn't give it to you on your all's final.
no,
No, definitely not.
no, you absolutely.
Oh, okay then.
That's
You did
bad.
talk about
It was-
Gaussian something.
Well, guess what's going to be on homework number 4? I'm not going to put that on homework 4.
Oh, shoot.
Here, basically you go take a real polynomial, you map it to the complex numbers, f of p of x equals p of I. You take your polynomial, you replace all your x's with i's, boom. That is a ring homomorphism that is onto, and whose kernel is the ideal generated by x squared plus 1.
So, is corollary to this that fields don't have irreducibles?
Correct. Yes. I mean, you could also just say that every element in field is either 0 or a unit, neither of which, according to the definition, is allowed to be irreducible.
Yeah.
So that would be a little bit more of a roundabout way of saying it, but yes.
Okay.
Yeah, fields do not have irreducible elements. There's very much a reason why our go-to examples are integers and real polynomials and not rationals or reals by themselves, because there's no irreducible elements to speak of in a field.
So when we're saying something is maximal, or basically within that ideal, you're saying that there's multiple generators of that ideal, and we're trying to find the largest generator?
What I'm saying is, if you look at this set of elements, there is no set of elements that contains there is no ideal in your ring that contains all of these elements and more other than the entire ring itself.
So for Rx,
Mhm.
you're saying that x squared plus 1 is the maximum of all that?
It's a maximum. It's the ideal that it generates is a maximum ideal, and that there's no way to include more elements in it without getting the whole ring. That's not to say we couldn't have something like x squared plus 3, where this would generate a completely different ideal from this one.
Yeah.
Both of them would be maximum ideals, and that you can't add more elements to it without getting the whole ring. And they both have like the same number of elements per se. It's not maximum in terms of just sheer number of elements. It's maximum with respect to like set inclusion.
Alright, so are they even like isomorphic too?
Yeah.
Okay.
These would form isomorphic subrings of this thing.
So it's like kind of like of those elements being generated, there's like no more that can be added in.
Correct.
Okay.
Yeah. How about we do a counterexample, and then maybe it'll make a little more sense. So let's do a quick counterexample. Same ring. Does anybody have a favorite? I'm not going to ask anyone. I'm going to ask Andrew. What's your give me a non-irreducible real polynomial, and don't make it 0 or a unit either.
X squared minus 1.
X squared minus 1. That's a good one. X squared minus 1. I claim that is not irreducible. Why is that? Why is x squared minus 1 not irreducible, Eleanor?
Because you can factor it to x plus 1 and 1, which are both non.
I can't believe I'm actually saying this, but I didn't quite hear that. Can you say that again?
You can factor it into x plus 1 times x minus 1, both of which are non-units.
Yeah, exactly. This factors into 2 non-units, therefore it is not irreducible in real polynomial land. So according to this theorem, that's the same as saying the ideal generated by x squared minus 1 is not maximal. In particular, what would be an ideal that properly contains this one, but also is not the entire ring? So in other words, what would be an ideal I could put in this blank here?
Is it generated by either x plus 1 or x minus 1?
Bingo. Yeah, because anything that is a multiple of x squared minus 1 is necessarily going to be also a multiple of x minus 1 as well. It's also going to be a multiple of x plus 1. But you can have things that are multiples of x minus 1 that are in this ideal without being in this ideal. Like 2x minus 2, for instance, would be an element here, but would not be an element over here. So that's what it means to say this one is not a maximal ideal. The fact that we can form a bigger ideal, there's an ideal that properly contains it, that's not the whole ring. Whereas over here with x squared plus 1, we can't do that.
I like maximal ideal better because it makes more sense that there are multiple maximal ideals instead of there's just A maximum.
Gosh, Emily Rose, take discrete math. Learn about the difference between a maximum element and a greatest element. Greatest implying it can't be, it has to be the only one if there is such a thing.
You mean like the greatest common?
Yeah.
Yeah, just like the greatest common divisor. How we talked last week about how there's only ever one of those, right?
It's
Up to a unit multiple.
Maximum.
Well, just wait until you find out what a unique factorization domain is here in a second. And this, by the way, is also equivalent to saying if you take real polynomials, you mod out by ideal generated by x squared minus 1, this is not a field. There's cosets in there that don't have multiplicative inverses. Is what?
We stifle them instinctively.
So any questions about what this theorem is saying? I mention this because this is a result we're going to use. It's proved in the book if you want to see it. I don't particularly want to go through a proof because I feel like we have more relevant things to do. Okay, going once, going twice. Sold! Awesome. So, all right, here we go. UFDs. UFD is a ring in which all non-units can be uniquely factored into irreducible terms. Where unique has like 5 asterisks attached to it. Because units really muck up these definitions. So a unique factorization domain, that is the only time you'll ever see me handwrite that word, or that phrase, I should say, is an integral domain. In which, for any non-unit, A, non-unit, non-zero element, in your UFD, first of all, there exists some finite number of irreducible terms that multiply together to give you A. And second of all, if you have 2 different ways of writing A as a product of irreducible terms, they have to be the same. So A equals P1, P2 up through P sub K, and that's also equal to Q1, Q2 up through Q sub M, are 2 factorizations of A into irreducible terms. Meaning here all the P sub I and all the Q sub J are all irreducible. And 2 things have to happen. First thing, K equals M. They have to, if you can factor A into irreducibles in 2 different ways, you have to have the same number of irreducible terms. And there exists an ordering of the Q sub I. So that for each I, P sub I is equal to U sub I times Q sub I for some unit U sub I coming from your domain D. Okay, that's a mouthful. What it really comes down to, there's every element, every non-unit can be written as a product of irreducibles, and it's unique the way you do it, other than the fact that you can always reorder the terms. So dir 6 can be written as 2 times 3 or 3 times 2. That doesn't count. And you could also have units get mixed in. Her dir 6 can be negative 2 times negative 3 or 2 times 3. So let's look at a couple examples. Let's do an integer state. Let's go with 60. Does anybody have? Oh, hi, Jonah. Nice for you to join us. Hey, Jonah, how would you factor 60 into primes?
2, 2, 3, 5.
2, 2, 3, and 5. I'm impressed. That was quick. Yeah, you could write it as 2 times 2 times 3 times 5. And in fact, that is the only way to factor 60 into primes.
But -2, -2, -3, and -4.
Oh, that's too simple. How about -3 times -2 times times -5 times -2?
That's what I said.
No,
You
you
just
had it in a
switched
different
it.
order.
You had 2, 2, 3, 5 still.
Everything's up to reordering.
So so these are essentially the same according to our definition, and that there's the same number of irreducible terms. But Dr. Gerstle, what if I put these in front? Those aren't irreducible, those are units, units don't count. So there's no way to write 60 as a product of irreducible integers in a way that doesn't use 4 of them. And also, no matter how we do this, there's always going to be some way of kind of matching irreducible terms here and irreducible terms here. For instance, we could match these two, these two, these two, and these two in a way so that all the terms in matching pairs are just unit multiples of each other. Specifically, this is a unit multiple of that, that is a unit multiple of that, that is a unit multiple of that, that is a unit multiple of that. And other than the fact that we can multiply by units, and other than the fact that we can reorder terms however we want, the factorization is unique in integers.
Are we still using the definition of unit as like
Something with a multiplicative inverse.
Okay, so -2 would. Oh, because you're saying it's in Z. Okay, I see. Alright, okay.
Yeah, this is over the integers. Over the reals, we couldn't do any of this because there are no irreducible terms, but everything's a unit anyway, so technically, the reals are a UFD. Because it is true that for all non-zero, non-unit terms in the reals, or any other field, it is true for all 0 of those elements that these conditions hold true.
That's how we end up with fields being because I guess
Yes,
that's why I asked.
Because fields,
earlier.
fields are UFDs, just kind of in a vacuous, trivial, not actually really telling us anything sort of way.
All the things we call UFDs, all the things we call fields, but technically.
Let's do an example over, do a polynomial example.
More sets with 1 unit.
What's the one I went with? Let's go with, I don't know, about 3x to the 4th minus 3x squared. What would be a way that we could factor that into irreducible terms? Yeah, irreducible terms. Bart?
Well, first I want to look at 3. We could take 3 out of there, we would left with x to the 4 minus x squared, but that could be factored into x times x minus 1 times x plus 1.
Like that?
I think so.
That's your way of factoring this into irreducibles?
Yeah,
I don't like it.
why?
Lincoln, why don't I like it?
Because 3 is
It's a unit.
yeah.
So we don't want units. I want a product of irreducibles, not irreducibles in units.
Just to raise the
How about that?
Oh,
Does that work for you, Parker?
yeah.
All right, we've written 3x to the 4th minus 3x squared as a product of irreducibles. Isaac, see with you had your hand up. What would be another way to write this as a product of irreducibles?
Well, at this point, it's just do like negative x times negative 3x. That's x plus 1.
Oh, now you're being boring. How about this one? Let's do 2x. Let's do 2x plus 2 times 1/2 x times x times 3x minus 3.
Someone teach you like simplified fractions when you were in elementary school.
Hey, this ain't an elementary school. I'm not teaching elementary school students this stuff. I'm teaching elementary school students, man. A couple weeks ago, my mom had me zoom in to teach a 4th grade math class, college math.
What did you teach them?
How to add matrices.
This would be hard to get to in elementary schools. They should learn more.
Yeah. Well, I mean, like 8th grade.
I think they should learn different.
All right, so if you notice, there's the same number. If you notice, there's the same number of terms here, and we can match pairs up from the first factorization and the second factorization in a way that makes everything unit multiples of what it's matched to. So, Pete, what could we match up 3x to?
To x.
Okay, that would be one way of doing it. Isabel, what could we match up x to? And you can't match x to x because Pete's already claimed that one.
1/2 x.
1/2 x. Andrew, how about x minus 1?
3x minus 3.
And Matthew, how about x plus 1? 2x plus 2, good job.
I give it to Lydia.
Lydia, what about that one? Good job, Lydia. Alright, sounds good. I don't applaud her, it's not that impressive. She literally had no other choice. Yeah, you notice 3x and x are unit multiples of each other. 3 is a unit in this ring. X and 1/2 x are unit multiples of each other. 1/2 is a unit in this ring. These are factors of 3 apart, again a unit. These are factors of 2 apart, again a unit. So it all checks out according to this definition of what it means to have a UFD. And there's lots of other ways of doing this. In fact, there's infinitely many ways in this ring of writing this as a product of irreducible terms. But you're always going to have 4 of them for this particular polynomial. If I've given you I'm not implying everything has 4. It just happened that way in both examples. But for this particular polynomial, there's always going to be exactly 4 irreducible terms when you factor it. And they're always going to be able to be paired up in this way.
Does the fact that it has 4 have anything to do with the fact that it's a degree 4 polynomial?
Yeah.
Oh, hey, how about that? No.
Really? Wait, no.
No, wait, no, that's cheating.
All right, how many irreducible, or if we want to factor that into irreducible terms, how many factors are we going to have? Aw.
Other than that,
Yeah,
so
but what if
it's an
it's
if it's a non-irreducible degree 4 polynomial, will it have 4 terms?
A non-irreducible degree 4 polynomial, no, because I could do,
In the complex of the word.
Okay, it's gonna be 4 or less though.
The problem is you have to.
that can be multiplied into x times x squared plus 1.
Too complex.
However,
Too
as Isaac
complex
is,
irreducible.
I was going to say, however, as Isaac is mentioning, over the complex numbers or any other, wait for it, algebraically closed field, that would be the case, yes.
Okay.
That the degree of your polynomial would match up precisely with the number of irreducible factors it has.
Well, here it's just the degree or less, isn't it?
An algebraically closed field, by the way, is one in which every polynomial can be factored into linear terms. The complex numbers being by far the most famous example.
Are there others
Oh, there's many other examples.
that don't have to do with complex?
Pick your favorite. Pick a field other than the complex numbers. Oh my gosh! Emily, Emily Rose, give me a field other than the complex numbers.
The real numbers.
Give me a different field than either of those.
The integers.
That's not.
That is not a field.
No, right, that.
Integer column.
How about the rationals? Let's go with that.
Oh.
Oh, you mean the quotient for.
The algebraic closure of the rational numbers.
What about
What
Z?
It turns out, okay, this is getting a little bit far afoot, but this is fun stuff that that we might talk about late in the semester if we have time. Given any field, there exists a minimum extension of that field. That's something we're going to be talking a lot about. Meaning another field that contains it, but is as small as it has to be, that is algebraically closed. So the algebraic closure of the rational numbers, for instance, would be such a field. Emily Rose, the reason why I didn't let you say the reals is because I wanted a different example.
What about Z mod 109Z?
What does the algebraic closure of
Is
rational?
that correct? Well, that's for you to discover. It's like basically like a subfield of the complex numbers that contains the rational numbers and only what you need so that things factor nicely.
Can you give the algebraically closed field definition again?
It's an algebraically closed field if every polynomial with coefficients in that field factors into linear terms. Every non-constant polynomial. A lot of fun stuff you can do with algebraic closures, but take complex analysis this summer, and fundamental theorem of algebra says the complex numbers are algebraically closed. Hey! Any other questions or comments about what it means for a ring to be a UFD? How about integer polynomials? You said that's not a PID, but is it a UFD?
Because normal diagram, PID implies UFD.
Well, yeah, but PID implies UFD, so something that's not a PID could still be a UFD.
Oh.
Because it didn't say
Right.
UFD implies PID.
Right, I forgot to say it.
So, not that ring.
Reducibles are. Is it just all of the integers except for one negative one? Or is there? No, it's.
So the units here are just plus or minus 1 again, just like
Yeah,
the integers.
so then it's primes. So then it's.
Well, irreducible.
But that gets, you know,
Yeah, could be other things. Turns out, it's a UFD. In fact, you can show, it's not too hard to show. You can show that if R is a UFD, polynomials over R will also be a UFD. So the fact that the integer polynomial ring is a UFD basically just comes from the fact that the integers themselves form a UFD. Mainly coming down to the fact that the units are going to be the same in both rings. So you just have a lot more irreducible terms when you allow for polynomials, but the fact that the units are the same means that the same unique factorization thing happening should still work, as long as the ring of coefficients is a UFD itself.
Does it always? You're not gonna be able to do that kind of stuff in Z of X.
X squared plus
you,
1?
You only have two, not counting for order. You can you can just take things and flip them positive, negative. You can't like start throwing around where the numbers are.
Sure. This compared to that, sure. There's a lot fewer ways of writing things in irreducibles. Like if I gave you 3x to the fourth minus 3x squared, I would dare say there's only a finite number of ways to write that as a product of irreducible versus infinitely many here, because you could always just multiply this by any constant, divide that by the same constant, and it would give you a different way.
Sure.
But the fact that there's only a finite number of ways to do it doesn't mean that they don't satisfy all this still. Yeah, good questions. So, I want to prove that turns out all PIDs are UFDs. And that's what I want to prove. I'll be honest with you. We're not going to prove that whole theorem. We're just going to prove this part. Which I think is the more fun part to prove. Proving this, it's tedious, it's annoying, it's in the book. This, though, also in the book, but a little more fun. Because it allows us to talk about a special type of ring called an Noetherian ring.
Oh.
Breaks off from our diagram. So, let me tell you all about Emmy Noether. Arguably most famous female mathematician of all time. German mathematician, did a lot of work in commutative ring theory. Commutative ring meaning multiplication's commutative. First, I believe, female full professor in Europe at any institution. And in her honor, we have Noetherian rings. So let's take a look-see at these, because it's going to turn out that all PIDs have to be Noetherian, and we're going to use that as part of our proof that all PIDs are also UFDs. So a Noetherian ring is one where you can't keep making ideals bigger forever. So it's a commutative ring. Again, commutative ring just means multiplication is commutative, because addition is commutative in any ring. In which, given any sequence of ideals, I1 contained in I2, contained in I3, contained in I4, contained in ... Eventually, the chain has to stop. You can't have an ideal, or meaning eventually all the ideals are going to be the same. So, for any sequence of ideals, ... there exists some n in the natural numbers such that for all k greater than or equal to n, I sub n equals I sub k. So eventually, what we're saying is this chain has to be of the form I sub n is a subset of I sub n is a subset of I sub n is a subset of I sub n. It can't keep getting bigger and bigger and bigger forever without eventually just becoming constant if you have a sequence of ideals. So what would be an example of such a ring? Well, I'll give you a hint. Any finite ring will automatically satisfy this because there's, just a finite number of ideals, period. I'm a little more interesting. Let's go with the integers. Ideal generated by, I don't know. Let's go 16. So 16z. What would be an ideal that properly contains 16z?
4z.
Oh, you're skipping right to 4z.
Oh, well, I can say.
Well, Eleanor wants 8z.
I don't want to do it.
Well, I don't want you in my class yet. Here we are.
I'll roll on out.
Roll out. So yeah, 16z is properly contained in 8z, which is properly contained in 4z, which is properly contained in z. I'm doing that on purpose just to spite you now, because I'm a spiteful man. Which, how can we keep going?
We can add to
No.
Z.
Well, no. Well, we can't do it with proper inclusions anymore. I mean, we could keep doing this forever, and it would technically still hold. But eventually you're stuck. You run out of ideals that keep getting bigger and bigger and bigger in this ring.
What does that slash mean underneath the
It's a proper subset of, meaning 16Z is a subset of 8Z, and they're not exactly the same because technically every set is a subset of itself.
and it's like you know that is a proper, like you can confirm it. So if you're like doing a proof, you gotta like.
If you're proving what that like.
Oh yeah, it's not like a not. Well, you have to. Prove
Yeah, it's
that,
like-
too.
It's like the equivalent of like a strictly less than.
Okay.
It's like saying less than or equal to, but you're removing the equal to.
Okay.
So yeah, you may have also seen like this notation.
Yeah.
It's just a little bit.
These mean the same thing, like is a proper subset of.
Okay.
I like this better just because it makes it blatantly clear that like these are not equal. A little bit. Whereas this is like maybe you were lazy and just forgot to write that. Technically these mean the same thing.
It's like whether N is
It's zero mathematician.
Sure.
Turns
Turns out
What did you say? It's like if N includes 0 or not.
no, except that's stop being dumb. So doesn't matter what ideal you started with here. There's only ever going to be a finite number of times you can get bigger before eventually you run out of ideals to get bigger in the integers. Like even if you started with something with like 150 factors, well then at most you're gonna have Then at most you're gonna have 150 terms in your chain unless you have some equals to in between before it eventually runs out. Hi, Vin. Any questions or comments about that? So, how about real polynomials? Real polynomials gonna satisfy that?
No,
You can make a chain that keeps getting bigger forever in the real polynomials?
I think so.
Explain how.
Oh. Oh, yeah, because, right, because 1/2 is properly contained in, no.
Are you taking the ideal generated by half?
No, I'm pretty sure it doesn't work. I just have a.
Let's think about it this way. Start with x to the 4th minus 1. So, that's x squared minus 1 times x squared plus 1. We can factor that into x minus 1, x plus 1, x squared plus 1 if we wanted to. What would be an ideal that properly contains that one? X squared plus 1. I'm going to go with the other one just so we can keep it going a step longer. Because anything that's a multiple of x squared minus, anything that's a multiple of x to the 4th minus 1 is also going to be a multiple of x squared minus 1 necessarily. Jackson, what would be an ideal that properly contains x, the ideal generated by x squared minus 1?
How about x minus 1?
Ideal generated by x minus 1. Yeah, anything that's a multiple of x squared minus 1 has to be a multiple of x minus 1, but not vice versa. Isabel, how could we get a bigger ideal? Or can we not?
I don't think you can.
I think we can. I think there's one way to.
Throw another term into the ideal and their generation.
There's one way to.
You could always just take the whole ring. But it turns out at this point, and then you get stuck. There's no way to make this bigger. You could just keep saying it's a subset of itself forever, but it can't get any bigger.
So you can't throw in like a comma x.
Well, keep in mind, this is a PID, so every ideal is generated by a single element.
Yeah.
So if you were to throw in, you could throw in like this. That's just the whole thing.
Well, thanks.
Yeah, because if it contains both of these things, then it has to contain their difference, which is -1. And if you have -1, then you have to have 1. If you have 1, then you have everything.
That would at least be a strategy that you could use
Sure.
to see if it applies.
Sure, you could always throw in more elements. And if you're working over something that's not a PID, that would be a way to do it.
Hint, hint.
So, for instance, we're trying to do this over again. Polynomials. Let's say I started with x squared.
Okay.
Isaac, how could we make this ideal bigger?
Well, I just want to throw in like 2, and then
Okay.
then you can throw in 3,
And then you want to throw in 3 in
5.
addition, and then 5.
and then
Great, you can do that. Except at this point, I'm going to stop you because that's the whole ring. Because if you contain all of these, then you contain 3 minus 2, which is 1, and then that's the whole ball game.
okay.
Turns out, these are all Noetherian.
Well, it's a pretty like
So
you have to find an infinite sequence of distinct things that are all in a certain order. That's not exactly anything.
So prime.
Wait,
like what?
Well, I tried primes.
Oh no, what if you just had a set only having primes?
Which is why it's kind of hard to make. Yeah. So, Emily Rose, one question before we talk about what would be a non-Noetherian ring.
I'm confused about the x squared in the whole ring, and I get that because it has 1 in it, that it's the whole thing. But would I be able to say there's another one in there that's x comma 2? Like
Sure, you
in
can go.
between?
Sure, you can throw in like that. That wouldn't be the whole
Or
ring.
like between x, would x squared comma 2 be a subset of x comma 2, right?
Yes.
Okay, that makes sense.
Yeah. Well, if you would x squared comma x comma 2 would give you the same thing as x comma 2. Yeah, that would be another way. And then at this point, you would get stuck because
The next bigger thing is the ring.
there's no way to make that bigger without getting the whole ring. That I'm
Wait,
pretty
no,
sure.
what about just x?
Oh, but what about just x? Does removing 2 make it
Oh.
bigger, Eleanor?
Oh,
True or false?
wait.
One of them has no context.
Oh, no, yeah.
Yeah. These, yeah.
Oh, but x1.
Other way around. Other way around, but not that. Not the way you
Oh,
want
but
it to
x
be.
comma 1 is like, never mind.
Well, x comma 1 gives you, yeah. Anytime you get a unit, you get the unit will always give you the whole ring.
But if you plugged in 4 instead of 2, then you could go even further.
Well, I mean, this would be different. Like these.
Yeah, I know, but instead
Yeah.
of plugging in 2, if you
Oh, I see. Plug in 4 and then plug in
Or
2.
plug in
2.
6,
Sure.
because then you just keep going.
Yeah.
There's lots of ways to make longer strings, but you're never going to make an infinite string of proper containments.
Yeah. What if there's infinite variables?
Say what?
What if there's infinite variables?
Yeah, what if you have x and y?
Yeah, so how about that? Let's look at an example of a non-Noetherian ring.
Yeah, that's what
How about we get spicy? Oh, you're going to love this one, Martha.
Oh, you're gonna do x and y?
No.
Is it gassy?
No.
Oh.
How about a polynomial ring, except instead of just one variable that we can have in our polynomials, we have infinite.
That's a lie.
So like a polynomial in here might be something like, I don't know, 2x, 5x, 800 squared plus 30x sub 2 x sub 9999998. We'll cube that term. Minus 8. That would be an element of that ring.
So many possibilities.
It's a big ring.
Wow.
Question, how big is it, cardinality wise?
It's
Really
not as
big.
big as you'd think.
Not as big as you think. It's actually only the same size as the integers,
Yeah.
cardinality wise, but turns out this is going to be a non-Noetherian ring. Why? Because here it is possible to make a string of ideals that keeps getting bigger and bigger and bigger over time. Because you could just take ideal generated by x1, is properly contained in ideal generated by. Let's see if I can get you to just say x2, and so I can say wrong. No, you got it. Which is properly contained in the ideal generated by x1, x2, and x3, which is properly contained in ... So that would be an example of a non-Noetherian ring. But pretty much every other ring we've seen in this class so far, and that I'm guessing you've seen in Math 410, was a Noetherian ring. All right, Eleanor. Is this a UFD? Ooh, I should put that on homework. Maybe that could be a homework question.
Wait,
What?
so
Is this thing a UFD?
Well, if it's hard enough
No.
that she has to like think about it.
I
Oh, if Eleanor has to think about it, that it's impossible for us mere mortals. Is that what you're saying?
If you asked her the question as if you can answer it, just like off.
Well, keep in mind that like whenever we talk about single elements in this ring, it's only going to have a finite number of terms.
Yeah, I feel like it will be a UFD if Z mod X is a UFD. Or not Z mod
It
X.
took
sorry,
her a full like 15 seconds to answer that. How could I make that a possibly make that a homework question? Turns out that is 50.
Cool.
And essentially, it comes down to the fact that the integers are a UFD.
Yeah, because you said that those, yeah, by that.
Well, this doesn't necessarily. This implies that adding any finite number of variables would make it a UFD, but it doesn't say. It doesn't prove infinite.
But you can use that to prove it. Probably.
Now Eleanor's getting back to her real self.
All your time I can be.
Any questions or comments about what a Noetherian ring is? Yeah, John.
With that, could we have a term with all of the X's in it? Like a
Well, don't
I'm
they,
asking myself because there exists a ring where you can.
well, don't they all technically have them just multiplied a lot of them by 0?
Well, no,
No,
because
no,
not as
I'm saying
factors
with
of
the-
each
I'm saying with the
individual
terms.
term.
Oh.
I mean, you could have like a plus 0 x1 plus 0 x2 plus 0 x3 plus 0 x4, but not times.
Oh.
I think in this ring, Jonah, the answer is
Zero, aren't they?
no.
That's very sad.
But there exists, but like if I were to do like, I don't know, replace these square brackets with parentheses, the answer would be yes.
What?
Whoa,
What is that?
I don't know, that is something else we're gonna be seeing in a month from now.
Are you gonna throw another loop at me with this whole like notation garbage?
Oh, well, if I throw the parentheses in, then we could also have, you ready for this?
Excuse me?
They have units now. Why are
Is
they
that a
unit- why are
lambda
they
or an
units
X?
Units?
Wait, no,
Yeah,
because
it's
you
not
have
a
one.
You
of
mean
the
like-
X6.
Is that a lambda
Because
or an
X-
X?
Like
That's an
X6
X.
is now a unit. Or in
Definitely a
multiplication.
laptop.
Oh no! Yeah, that makes it a field.
Weird.
It is.
Does it make it Noetherian or no?
Alright, this is getting very far fuzzy.
Yes.
Like, let's get back on topic.
It is in theory.
Look at
Everybody-
look at
The next
lemma on
page.
the next
Oh,
page.
right.
So if you look at the next page, and this is. Let's start this. Oh no, class ended 4 minutes
Oh,
ago. Oh no.
no.
Let's see if I can prove every PID is necessarily Noetherian. That, by the way, is not a PID. Doesn't mean it's not a UFD though. And this is going to be part of our, and this is going to be a lemma to our bigger theorem that every PID is a UFD. We're going to use the Noetherian property along the way to help us get there. And turns out this one's not so bad. Basically, we're going to assume we have a PID, and we're going to assume we have some infinite chain of ideals, like in the definition of a Noetherian ring. And then what we'll have to show is that eventually that infinite chain will constant out, so to speak. So we're going to let R be a PID. And I1 contained in I2, contained in I3, contained in ... be an ascending chain of ideals. By the way, we call this an ascending chain because it gets bigger. Yes, you can have descending chains as well. And if you flip it around, you actually get something called an Artinian ring instead of a Noetherian ring. And it's a lot easier to find non-Artinian rings because you can just take the integers. We're going to let this be an ascending chain of ideals. And our goal is going to be to show that this chain can't keep getting bigger forever. Eventually, you're going to get to a point where you can't get any bigger because you've reached the whole ring. So here's how we're going to do that. I claim if we take the union of all of these.
Oh my gosh.
Oh no, it's like real analysis.
I've been doing
Wait,
I claim this is an ideal in what I call a bar. So
Shouldn't that be R?
shouldn't what be R?
Like
R
the
is
union
the
of
ring.
them is going to be all of R.
I didn't say that.
But it should be.
Not necessarily.
Why not?
If you never make it to R, it's
It
not
could start with
necessarily.
Yeah, it doesn't have to make it talk. We're not assuming. I don't want to assume that this chain has to end to start with, because that would be like assuming what we're trying to prove.
No, I know, but why would it stop any earlier than R?
I mean, you could just have it stop any earlier and just keep going with the same one each time.
Yeah,
Oh.
exactly. Yeah, I never said prop. Yeah, we're not forcing proper containment on this chain of
Oh,
ideas.
right. Okay, so if you did that, then they would have.
Ideally.
Then it would be tricky,
Yes.
but not necessarily. It wouldn't necessarily give you the whole thing, as we've seen. So that's my claim. Question: is there anyone who hasn't seen this sort of union notation before? We technically haven't seen it in this class, and it's something that tends to show up a lot more in like real analysis type classes than abstract algebra. But basically what this just means is take the set of anything that's in at least one of these ideals and toss them together. It's an axiom of set theory. So how do I prove something is an ideal? And get something inside of it? That's part of it.
Yes.
What else do we need? Other than that, it has superclosure under multiplication. Does Eleanor remember the subring test
It
from
has
410?
one? No.
I'd have to contain one.
No, because then it's the whole thing.
In fact,
It contains
I hope it doesn't.
0.
Well, it has to contain 0, but that's part of the supermultiplication property because
Right.
it has to be closed under what other operation besides superclosed under multiplication? Yeah, but that's not enough. Subtraction.
Yes, I do remember this.
Yeah.
It
So-
makes me excited.
Okay.
So there's like a theorem. So there's a theorem that in order to prove something's an ideal, if you want to prove this, you can prove two things. That it's closed under subtraction, meaning if A and B are in the ideal, then A minus B has to be in the ideal. And finally, the supermultiplication property, if A is an element in I and B is anything in the ring, then AB has to be in the ideal. Fortunately, we can prove these two things fairly quickly. For subtraction, we can say that if A and B are any two elements in our ideal I, well, since I is made up of the union of all of these ideals, I1, I2, I3, going on forever, if A and B are elements in the union, then there has to be some ideal in this chain that contains A and some ideal in this chain that contains B. So we can say then A is going to be an element in I sub k, and B is an element in I sub j for some I sub k and I sub j in the chain. Woolog greater than or equal to j. And then in that case, then if k is bigger than j, then I sub k is going to contain I sub j. So then I sub j is going to be properly contained in I sub k. So a and b are both elements in I sub k.
Yeah,
Not necessarily.
it can't, right, it,
Yeah, they could be proper, but it might not be. Hence why I didn't put the slash in.
Yeah, but you said.
Oh, did I?
Yeah.
Oh, well, I didn't mean it. So A and B are both contained in the same I sub k, which itself is going to be a subset of I. Or, no, actually, we don't want that yet. Hence, A minus B is also going to be contained in I sub k, which is a subset of I. So A minus B is contained in I. So that tells us that taking the union of all these ideals is going to be closed. That union is going to be closed under subtraction. Because you take any two elements in the union, they're going to both have to be in one of these ideals in the chain, and since we know everything in the chain is an ideal, or we're assuming that at least, then the difference has to be in the ideal, because ideals are always closed under subtraction. So that's the subtraction part. For the supermultiplication part, we're going to let A be an element in I, and B be some element from the ring R. And then, since I is an ideal, or since, then, well, oh gosh, I'm turning into Lincoln. Let me pause a second. Then, since I is the union of all the I sub k's, we know A is contained in one of the I sub k's, specifically one of the things in the chain. For some k. And then since I sub k is an ideal, A times B is going to necessarily be in I sub k and thus in I. I'm sorry, Lincoln, was that too much?
do you mean since the thing is in the thing, the other thing is in the other thing?
Yeah, like that. That's what I was that's the point I was getting to, and that's why I had to stop myself. So since I sub k is an ideal, we know AB is in I sub k, and hence in I. And there's our proof of the claim. We've shown that the ideal, we've shown that I, taking the union of all these things, is an ideal. Yeah. Notice that we haven't used the fact that we're working over a PID yet. All right, double time. So now we're going to use the fact that we're working over PID to say that, well, I is an ideal. It has to be generated by a single element. So since R is a PID, I is going to be generated by some element. I'll call it little s. For some little s in R. PID means all ideals generated by a single element. And then S has to be contained in I, which is the union of all the ideals in this infinite chain. So S is going to be contained in I sub n for some I sub n in the chain. But at that point, I sub n is going to be equal to I.
Whoa.
But then the ideal generated by S is going to be a proper or subset of I sub n by closure. Hence, I sub n equals the ideal generated by S equals I. And that tells us that after that I sub n point, everything breaks down. But everything has to be the exact same ideal because there's no way for it to become bigger without adding more elements than somehow the entire union of all of these things has, which is possible. So, then since I'll say I sub n is properly contained in I for any k greater than or equal to n, we know I sub n has to be, we know I sub k is equal to I sub n for any k greater than n. Thus, our chain has to stop at some point, and hence our radius of the union. Boom! All right. Have a good day, everybody. When we come back on Thursday, we will finish our proof that all PIDs are UFDs, and then move on to some other fun topics. Y'all have a good one. See you all on Thursday. Shut it down. Bye, Lydia.